let's look at matchings. This is one more problem we want to consider in the graph streaming context. A matching is basically matching M is basically a subset of the set of edges such that no two edges in the matching M share an endpoint. So let's look at one such example. So this is a matching. So this edge and this edge. And now if you look at so M is, in this case, M is equal to 1 comma 2 and 3 comma 4. If you think about it, why is this a matching? Well, it's a subset of the edges, and if you look at these two edges, they do not share an endpoint. The first edge has endpoints 1 and 2, the second edge has endpoints 3 and 4, and they don't share an endpoint, and so it's a matching. Let's look at another example, this one. This is another matching, but if you were to try and add one more edge, then it's no longer a matching. So this is not a matching. Okay, and typically we are interested in either maximum cardinality of the matching. So you want matchings that are of large cardinality, or in the weighted setting, maximum weight matching. So for example, this is a matching, but this is a matching of just one with one edge, and once you've included that edge, you cannot add any other edge. So this is not a maximum cardinality matching. So for this graph, the real maximum cardinality matching would be the following. So here you include, we already saw this, 1, 2, and then 3, 4. Okay, but let's look at an example of maximum weight matching. So for example, let's say that this is 3, 4, 5, and 2. Let's make that a little bit interesting. Let's make that 1. So now, what is the maximum weight matching here? If we include 3 and 1, we only get a maximum weight of 4. If we include the edge 2, 3, then also we get a maximum weight of 4. So really the maximum weight edge, the maximum weight matching is just that one edge 1 to 3, and that will give us a maximum weight of 5. Okay, so let's see how we can compute the maximum cardinality matching first. So first we're going to focus on maximum cardinality matching. So it's the unweighted setting, and we have to do this in the streaming model. So as usual, we start with the matching being the empty set, and then we ask, okay, how do we compute the maximum cardinality matching? Now we look at edges one at a time, and for each edge we first we check whether including the edge E into the current matching retains the fact retains the matching. Okay, the matching property. What is the matching property? No two edges in the matching should share an endpoint. If that property is violated, then you discard the set E, the edge E. Okay. On the other hand, if by including E you get a new matching, then you simply add that edge to the matching. So M, you simply assign M to M union this edge E. So, this is a very simple greedy algorithm, and this gives us a good matching, but it's not the true maximum cardinality matching. It's only an approximation, and a simple let's look at a simple graph where this algorithm will fail to create to give you the actual maximum cardinality matching. So, let's say the graph is of this form. You first get the edge 2 comma 3, then you get the edge 1 comma 2, and then you get the edge 3 comma 4. Let's say you get the edges in this sequence, then your m after the first iteration will be the edge 2 comma 3, and then anytime when you try to add the edge 1 comma 2, it will violate the matching condition because they share that the vertex 2. So, this edge 1 comma 2 will not be added. Then when we get the edge 3 comma 4, again we will discard that edge as well, because again it is a shared vertex. And so the algorithm will output a matching with just one edge. But simply looking at this graph, it's easy to see that the maximum cardinality matching is actually these two edges, 1 comma 2 and 3 comma 4. So, you get two edges in the matching. So, this is which means that we only could get half the number of edges, and as it turns out, this this algorithm is guaranteed to give you that sort of an approximation. So, two approximation which means that the number of edges output by this algorithm is going to be at least half the number of matchings in an optimal maximum cardinality matching. So, if the optimal maximum cardinality matching is say 100, then we are guaranteed to get some number of matchings that is sandwiched within this region between 50 and 100. So, in this example, the maximum cardinality matching was 2, and we got our algorithm is guaranteed to output some number of matchings which is between 1 and 2, and in particular we got 1. So, this is the maximum cardinality matching, and now let us move on to weighted case. So, here now we are looking at a weighted graph, and we are not looking at the cardinality, but we are looking at the maximum weight matching. Okay, we want a maximum weight matching, and the algorithm is a little interesting here. You start with, as usual, the empty matching, and we look at edges one at a time, and for each edge we look at we collect the set of edges in the current matching. So, this M is the current matching that we have. We collect the set of edges that have a common endpoint with the current edge. E is the current edge in our stream. And we ask if there are edges in the current matching that have a common endpoint with the most recent, the current edge in the stream, and we collect all those edges. And note, the question is, what is the cardinality of this set C? It must be at most 2, because the current edge, let's say, is E, and let's say it's between this is this edge E between U and V. M is going to be a matching. It's the invariant that this algorithm is going to maintain, and so so at best these two the set C could have one edge incident at U and another edge incident at V. So the set C could have a cardinality of at most 2. Okay, and you look at that set C, and the weight, the W of C is basically the sum of the weights of those edges. So let's say this is 2 and this is 3, then W of C will be 5. Okay, we ask whether the new edge E, the current edge E from the stream, is good enough for us to include in the matching, because if we were to include E, then we would have to throw away these two edges. So before we include E, we want to make sure that it's worthy of being included, because that will mean that the other two edges have to be thrown out, right? So to do that, what we are doing is, well, your intuition might say that you just simply do that if this condition holds. If W of E is greater than W of the edges in the set C, then E is good enough. Okay, but as it turns out, that has a small problem. We'll look at that. So instead, what we are going to do is we are going to not just look for this condition. We will in fact expect a little bit more out of this edge E. W of E must be greater than W of C times 1 plus some parameter gamma. This is basically rewritten in this form over here. Okay, so if this edge E is good enough in this, according to this, in other words, if it obeys this inequality, then what we do is we throw away C. So we remove C from the matching and we include E into the matching, only if it is good enough. Okay, and we do this for every edge in the stream, and we finally return the matching M. And there's a little bit of analysis. If you with that analysis, you can show, and then for the right choice of the parameter gamma, you can show that this algorithm will actually be a 5.828 approximation. So now let's actually look at, let's revisit this condition. Okay. Why did we even have to add this 1 plus gamma? Why not just include an edge whenever it is better than the current competing set of edges, the set C? Let's think about it a little bit. Let's play with an example. If you look at this example, you just have your input graph G is a weighted graph that has n vertices, and the edges go from 1 to 2, 2 to 3, 3 to 4, and so on. And the weights are 1 plus epsilon, 1 plus epsilon, 1 plus 2 epsilon, and so on. So in general, if you have a vertex I and I plus 1, the edge between them has weight 1 plus I epsilon. Okay. Now let's suppose we use this condition. W of E is, if it is greater than W of C, then let's say that's all we have. Okay. So, and let's say we get the edges in this sequence. First we get this edge, second we get this edge, and so on. Okay. So what will happen is the following. We will first include this edge, so in the matching. Okay. And then when edge 2, 3 comes, we will throw away this edge and we will then include this edge. And then we will throw away this edge and we will include the next edge, so on and so forth. At the end, we would have thrown away all the edges except the very last edge. Okay. So under this condition, we will get a matching of weight 1 plus n minus 1 epsilon as the maximum weight. But let's actually look at this a little bit more carefully. The best thing, the highest cardinality, not cardinality, sorry, the maximum weight matching is can actually be a lot higher. It can include this edge, the previous edge would not be included, but basically every alternate edge can be included. And let's say this edge was included and this one was not included, and let's say this one was not included, but this one could have been included, and so on. Every alternate edge could have been included. So the actual maximum weight matching is going to be much higher than what the algorithm actually will output. So that's output under this condition. So that's why we need this this gamma. Okay. Okay. So that's what I would want to discuss about matching. We have one last notion that we want to compute using in the streaming model, and we'll do this is basically random walks. And of course we've studied random walks quite a bit in this course, and you may recall that the random walks are actually useful to compute something called the page rank, which measures the importance of vertices in a graph. And typically this is what search engines use to measure the importance of web pages in the internet. So random walks in that sense tend to be very, very important and fundamental to the business of search engines. And in fact it's an algorithm that was invented by the founders of Google, and which one of the key concepts that made their business so strong. So it's a very important notion of random walk, the random walks notion. And the question now is, if you have the entire graph, it's easy to compute a random walk. But if all you get is the graph in this sort of a stream, you get one edge at a time in some arbitrary order, then things become a little bit tricky. So how do you compute the random walk? And this is actually an example where your algorithm, for anything useful to be computed, one pass is not enough. You'll have to actually do multiple passes. So one pass is simply one for loop over all the edges in the graph. But can you to solve a problem like the random walks problem, one pass is not enough. You will need multiple passes. Okay. And what is a random walk? Well, you start at some vertex, say V0. Considering all of its neighbors, you choose one neighbor uniformly at random. You go to V1. From V1, you have a bunch of neighbors. You go to V2, V3, and then let's say back to V1. But just to sort of note that this was the vertex visited fourth, we are going to just sort of, for our random walks purposes, label this vertex again as V4, then we go to V5, V6, and then come back to this vertex. Now we call it V7, then V8, V9, V10, and come back and call it V11 and V12. Okay, so this is an example of a random walk. And so let's set up some basic notations. Suppose we start a random walk at a node u. Okay, the distribution. Now let's say we allow that random walk to make this walk, and we allow it to do t steps. Okay, after doing t steps, this random walk is in some location, and if you think about it, it's actually the location is a random variable. It can be one of many nodes. So in this example that we saw, after 12 steps we reach V12. But if you were to run this random walk again, maybe it would have reached this vertex, or maybe it would have reached this vertex or this vertex, or it would have come back to V0 itself. There are a variety of possibilities, and for each of these possibilities, there's a probability associated with after 12 steps, what is you can ask what is the probability that it will be the random walk will be at this vertex after 12 steps. What will the probability of the random walk reaching this vertex after 12 steps? That's another probability, right? And that's basically a probability distribution, and that we denote by mu t of u. It's the distribution of the random walk after t steps. Okay, and now essentially when you run a random walk for t steps, you're basically sampling from this distribution. Okay, and so now let's look at how we can find mu t of u. It's actually quite easy when you have t passes, right? In the first pass, you basically, let's say you start at u. In the first pass, you look at all the neighbors of u, and then after seeing all the neighbors, you pick one of the neighbors uniformly at random. Okay, so at the end of the first pass, you'll get the first random walk step. Seems a bit wasteful, but still, after t passes, after one pass, you can make one step in the random walk. Let's say u is nothing but the 0th element from v0. Let's say after the first pass we've gone to v1. Now in the second pass, you look at all the neighbors of v1 and simply choose one of them uniformly at random. You'll get to the second location in the random walk sequence v2, and so on. So you can do that for t steps, and you will get mu t of u. Okay, so this is pretty trivial, but that's pretty wasteful, and we want to do it better. And in particular, what we can see is we can actually sample from mu t of u using not t passes, but rather just square root of t passes. And the idea is to try and perform square root of t random walks in parallel and somehow stitch them together. So let's actually look at the algorithm. So for simplicity, to just focus on the concept rather than the details, what we're going to do is just look at a simplified version of the algorithm. It's not going to be complete, but we're going to just try and understand the concept behind this. Okay, so what we're going to do, so what we're going to do is just run this algorithm for t rounds, okay, t passes, square root of t passes rather, sorry, square root of t passes. So, but what we're going to do is for every vertex v, we're going to compute tv. What is tv? tv is a node sampled from mu square root of t of v. So, if you start at v and you run the random walk for square root of let's say square root of t steps, okay, then you will get you basically sample something from mu t of mu subscript square root of t of v. Okay, but we will do this. Importantly, we'll have to do this for every vertex v. Okay, so remember, we have at our disposal some O of n space. So with just constant space, we can do one random walk starting at one of the vertices, but since we have O of n space, we can actually do n parallel random walks, and for each one of them we do it for square root of t passes. So we'll get, for each one of them you'll get a square root of t length random walk. Now the important thing is to somehow stitch these these random walks to create a random walk of length t. So essentially what happens is the following. So from one of the vertices, say, let's say this is the u, vertex u, and let's say this is and this is u So let's say this is a set of all vertices. From u, you get t of u. This is basically square root of t length random walk starting from u. Similarly, we would have done this for all the edges. Okay. So, from tu is basically again one of the vertices in the graph. So, let us say that is nothing but say v1. The thing is this, we also have computed t of v1. So, what we can do is we can take this random walk and stitch it with this random walk. We will get a random walk of length 2 times square root of t starting from u. Okay. And we can continue this. So, now t v1 maybe that is nothing but this vertex v2. Okay. So, then we can take this and stitch it with the rest, and then you will get a random walk of length 3 times square root of t. Now, if you take square root of t such if you do continue to do that, you will get square root of t such random walks, each of length t square root of t stitched together, you will get a t length random walk. Okay. And so, just by stitching these short walks, we will be able to we will be able to compute a we will basically be able to sample from mu t starting from u. Okay. This is a t length random walk. So, this requires I mean, now the issue is this. So, now if in so doing, if we end up so let us say this ends up in a location and it happens to be again v1, we are in trouble because we have already used the random walk starting from v1. Okay. So, that is a little bit of a problem. So, that is why in this algorithm what we are doing is we are actually this line represents the stitchings that happened, but as we are trying to stitch, we should be going to distinct vertices and collecting short walks from there. If that is somehow not distinct, we will be running into some trouble because we cannot reuse the same short walk twice. So, that will be an issue which there is a little bit more work that can be done to avoid that issue. Essentially, by avoiding all of this, you will by overcoming those challenges, what we can say is that this problem can be solved with a space of O of n plus t requiring at most O of square root of t passes with high probability. And so, then you can use these random walks to then compute the page rank. So, that so just to conclude, so today we have looked at graph streaming algorithms. We have looked at a variety of algorithms starting from very basic things like testing for connectivity, minimum spanning tree, and then we looked at some non-trivial concepts in graph algorithms like graph sparsification, random walks and things of that nature, and we have seen how even in this sort of restricted model of streaming, we are able to compute these concepts reasonably well. So, with that we will conclude our lecture on graph streaming. Thank you.